Let's go ahead and look at all of our knowns for the situation. So we have the initial velocity of the raindrop at negative 15 meters per second squared. And we're going to absorb the direction of all of the parameters inside the symbol itself. So the velocity initial is negative 15, which is down. Um, we have the mass over time. So that's the mass of the rain that strikes the roof of the car per second. That's going to be 0.060 kilogram meters per second. And this is a certain amount of mass that is hitting the roof of the car over a duration of time. So it would be a certain mass m divided by a delta t right there. The final velocity as the raindrop goes splat on the roof of the car is going to be 0. And what they're asking for is the force, the average force that comes about from all of this. So first thing I'll look at is what equation equates these parameters together. So it looks like we got force, of course, which is what we want. We have velocities and it looks like we have a mass. Well, that kind of looks like momentum to me with the velocities and mass. And how force relates to momentum is through Newton's second law, but in a more general sense. Delta P over delta T. And this is an algebraic version of it. All right, so the definition of momentum is m times v. So we're going to put that over t here. When you have a change in two variables, that is equal to the change in one variable multiplied by a static second variable plus the change in the second variable times the static first variable divided by delta t. Now, it's hard to conceptualize this, but what we can say is that the second term, for example, simulates a mass of a certain quantity changing its velocity, which is exactly what's happening. We have a raindrop of a certain mass changing from negative 15 meters per second to a 0 meters per second. So this is good, and we happen to know those variables. Now, the first term simulates a raindrop that changes its mass, possibly by losing it through evaporation or some other scheme, going a particular velocity, not changing. Okay. This doesn't happen in this case. So, this appears to be, especially because the raindrop does not lose its mass during fall anyway, we're going to say that's equal to 0 since there's no change in that mass. So this now ends up being m over delta t times change in velocity, which is vf minus v naught. V naught is negative 15 meters per second. Vf is 0. And the whole quantity here is what we got in the beginning, which is 0.060 kilograms per second. And this ends up being 0.90 newtons. You'll see a lot of problems where two variables are mixed in together for a particular quantity that's given. So make sure you get that and you write it down as is. It might help you in the future, even if it's two variables mixed up. You don't know what the mass is, you don't know what the time is independently, but you do know what they are mixed up. So that's still helpful.